It's a great pleasure to introduce someone I've known for over 15 years now, Dr. Mark Huckvo from UCL. Mark originally studied physics at the University of Warwick before going to UCL, first of all, as a PhD student, to work on a project to do with computer-controlled audiometry, I believe, before I knew it. And then after finishing that, he briefly, for about 3 years, worked in the software industry before returning to UCL as research assistant, then research fellow, then lecturer, then senior lecturer in the department of what was then phonetics and linguistics, now part of the speech, hearing and phonetic sciences, where he's worked on various projects to do with speech technology and speech science, which extensively uses Fourier analysis. In his time there, he's published over 100 papers and supervised as main supervisor at least 8 PhD students, one of whom is speaking to you now. Many of whom have gone on to get good jobs. And so I think I'll leave it to Mark to impress you with his knowledge of Fourier and its analysis and its development. So Mark Huckvo.
Thank you, Gordon, and good afternoon, everyone, and thank you for inviting me. So some ideas in science are sort of born fully fledged, fully formed from the minds of geniuses, like relativity springing out of the mind of Einstein. But other ideas build slowly. They develop over a long period of time. They involve lots of people, and sometimes the genesis and the birth of these ideas are sort of lost in the mists of history. And the story of the Fourier transform is an idea like that. It's something that took place over a long period of time, from the 17th century to the 20th century. It involved probably most of the most famous mathematicians in that period. And so you'll see, along this story, a whole load of famous mathematicians too.
One of the screens has disappeared. These things happen from time to time.
It's gone off. Turn itself off.
We can use them.
Is everyone happy with that
Some standby.
It does this from time to time.
Are you okay? Can I start again?
Yeah.
We're
right over here.
I forgot to pick my umbrella.
So this story extends from the 17th century to the 20th century. It involves some of the names of those famous mathematicians over that period. It's a story of ambition, it's a story of jealousy, it's a story of genius, and it's also a story of some rather dodgy mathematics. So just to begin, I've got a mixed audience here. What is a transform? For a transform is just a piece of mathematical analysis. You've got a problem over here, you've got some measurements, some numbers, you want to solve a problem with these numbers, and you find that the problem is too difficult to solve in this area with the numbers you've actually measured. And the idea of the transform, it takes those numbers and it puts them over here into a different form. And your problem that you want to solve turns out to be easier to solve over here. And so you can transform your data, by transforming your data, you're transforming the ease with which you can solve the problem. With a bit of luck, after the transform, you can get a solution, and then maybe you can transform your solution back to the original domain, and you've got a solution, solution in the first domain. So the Fourier transform is probably the most famous and most widely used of transforms available in mathematics, and it's also, of course, very highly regarded. So here's William Thomson, aka Lord Kelvin, Glaswegian physicist. Fourier's transforms are only one of those beautiful results of modern analysis. It may be said to furnish an indispensable instrument in the treatment of nearly every question in modern physics. And so almost anything in the area of William Thomson's domain, he felt that the Fourier transform could be applied. On the other hand, William Thomson is not necessarily the greatest referee of ideas. In a 1902 newspaper interview, he said, "I don't think that airplanes are ever going to be successful as a means of transport." So you see Fourier transform in all kinds of areas of science. So when you're trying to compress data, when you're trying to look at the study of crystals or study of proteins, or understand seismic waves in geology, or look at the spectral analysis of stars, or in making magnetic resonance imaging images, or looking at compressing and encrypting signals. in studying diffraction and refraction and the structure of optical systems. And then this is my area, which is audio processing. So we're dealing with sound signals. But I don't want you to think from that that the Fourier transform is only applicable if you happen to have a PhD in physics or computer science. You'll find the Fourier transform in everyday applications as well. So you'll find it in your mobile phone. Every time you make a telephone conversation, it's in your satellite system. Every time you want to find out where you are on the planet's surface, every time you take a digital photograph, every time you watch a movie on a DVD, and any time you're watching streamed multimedia on iPlayer. So next time you're going to watch Top Gear, that's not a good example. You'll be using the Fourier transform. So where do we start from the story of the Fourier transform? I like to start all of these kinds of stories in 1642. My favourite history of science, because 1642 is the death of Galileo and the birth of Newton. Happened in the same year. And so in a way, that 1642 is the boundary between the Renaissance science and modern science. So why do we think of Newton as being the birth of modern science? Well, it's because he takes the view that the mathematical description of physics, the mathematical description of reality, is a way of understanding reality. So Newton, 1642 to 1727. Of course, we also associate with him with the invention of the infinitesimal calculus, and of course we also have to at that point mention Leibniz. I mean, Newton had better PR than Leibniz, so we tend in this country anyway, we tend to think of Newton as being the inventor of calculus. And the point is that you could start the mathematical techniques that were being developed by Newton and Leibniz could be applied to real physical problems like the movements of objects and gravity and optics and heat flow and movement in general. By the time of, say, 1727, which is when Newton died, those ideas had really spread throughout Europe. They were being taught in universities right the way across Europe. They were being very well established. And people were taking these ideas of Newton and Leibniz to apply differential equations to solve problems with measurements that are changing in space or changing in time. For example, not only sort of dynamics that Newton addressed, but bodies, extended bodies, which had not mass concentrated at a point, but mass is distributed. Looking at materials that are elastic, that deformed in shape, and so that their densities and their pressures changed, or studying the motions of sound. So the first person that we're going to meet in our story of the Fourier transform really starts at the beginning of the 18th century, and he decided that he'd follow on from this idea of applying calculus and differential equations, but he'd applied it to the problem of the vibrating string. And his name was Jean-Baptiste Laurent d'Alembert. And d'Alembert was born in Paris. He was an orphan. He was abandoned on the church of Saint-Jean-le-Rond in Paris, and that's why his name has got Laurent in his name. He was abandoned as a baby on the church and taken in. His father secretly managed to pay for his education, and he trained to be a lawyer. But he also had this hankering after mathematics, and he started to study this particular problem of the vibrating string. And in 1747, he published a treatise on researches on the curve that a tense chord forms when set into vibration. So let's have a think about the vibrating string and the way in which d'Alembert addressed that particular problem. And we'll see how it relates to the Fourier transform as we go through. So here's a vibrating string. I have to have brought one with me. It doesn't, just like put it on the, you can't actually hear it. Okay, so I've got a vibrating string. What's interesting about a vibrating string, if you're going to try and solve it mathematically, compared to what I've done before, is that a vibrating string is clearly an object which has an extended mass along its length, which makes it more complicated to deal with than a point mass. And when the string vibrates, different parts of the string vibrate differently. So the middle part of the string here is vibrating more than the ends of the string vibrating. And that means that whatever function is that we're going to use to describe this vibration is going to be a function of distance. So it's going to be a function of space. But also this vibration, in fact it is a vibration, is clearly also a function of time. The location of the string at any particular point, it also changes with time. So immediately we've got a problem. This is one of the first times when we're trying to apply differential equations to something which is both a function of space and a function of time. And the way D'Alembert addressed it is very similar to the way in which you might do it today. He said, well, let's just assume that what we've got is two functions multiplied together. One's a multiplier, one's a function of space, and one's a function of time. We're just going to deal with them separately. So that's fine. So that's how D'Alembert started to approach the problem. So typically, he starts off by writing down the differential equation that he needs. So he takes a displacement of the string, he works out the forces, takes up the mass of an infinitesimal element and looks at the forces that way, and sees and writes the equation for the movement of each individual component of the string. Now, if any of that is familiar to any of you, you end up with a differential equation, then you've got absolutely no idea what to do next, which is basically you've got to try and find some kind of a function which satisfies this differential equation. And there could be an infinite number of analytical functions that you might use, and you've just got to hunt around and try and find one that might be a solution to that equation. And this is this problem that D'Alembert had. So he said, well, what do we know about the vibrating string? So he said, okay, if I've got an infinitely long string and I displace it, then obviously that displacement will go back to the middle again. But obviously these displacement waves, one wave will shoot off in that direction to minus infinity, and one wave will shoot off in that direction to plus infinity. And so effectively I start with one displacement and I end up with two waves traveling along the string in opposite directions. Now imagine I've cut the string so it's now a particular length and it's now fixed at these 2 points. Then when this wave goes this way, it's going to hit that end and it's going to bounce back. When this wave goes this way, it's going to hit that end and it bounces back. And it's quite easy to show that when this thing bounces back, it also turns upside down. So that the wave that's positive going this way hits that end, and then it's negative when it comes back this way. The wave that's positive going that way flips up down, and it's negative when it comes that way. These waves then cross, and then this negative one flips around, becomes positive, comes back this way, this one flips around, comes positive, comes back this way, and then we're back to the beginning again. If you think about it. So we're back to the beginning, right where we started from, with exactly the same displacement where we started. All that happened is we sent two waves that way, they bounced like this, and they came back together again, and we're back at the beginning. So he knows that whatever function it is that solves these differential equations, there's going to have two really important properties. And those properties are basically the idea that this shape of this travels along the string, bounces around, comes back here. That thing must be periodic in twice the length of the string. In other words, if it's got a particular value here, at some particular point in the string, some particular point in time, by the time it's bounced that way, come back, it's gone a distance of 2L, twice the length of the string, and it's come back to where it was at the beginning, where the whole thing starts again. So whatever function this is, it must have a period of 2L. And the other part of this is that it must have, when this thing reverses, so it's going this way, and then it comes back the other way, it must flip upside down. In other words, whatever this symmetry this function has, the function, if you run it backwards in time, it must be as if you flip the function upside down. So let's just have a look at some vibrating strings and see how that works. So here's our static vibrating string, and we set it vibrating, so that it's just looking at the actual movement of the string itself. And now if we imagine what these two waves are, one wave going one way and one wave going the other, then with a bit of luck it will look like this. So you'll see a pink and a green wave. And really what's happened is that the dark blue wave is the sum of the pink wave and the green wave. And the green wave, and sort of the one wave is going one way, one wave is going the other way, and then once the wave hits one end, it flips upside down. So just follow, say, the green wave there, flipping upside down, and it comes back the other way. Okay. So D'Alembert has these differential equations, and he has this idea that he's looking for functions which are periodic in the length 2L, and which, when you run them back in time, they flip upside down. It turns out that this time in history is also about the time in which people have thought about sines and cosines as being generic functions rather than just being something to do with trigonometry. So we learn about sines and cosines when we think about triangles and the angle between the adjacent and the hypotenuse and things like that. But at this particular amount of time in history, it's just when people are saying that really a sine is just a function. You pass any real number into the sine function, you'll get some number, you get some value between 0 and 1 out, minus 1 and 1. And so he sees this function. Here's a really good function for D'Alembert. Here's a function that you can see is periodic in 2L. It goes from -1 to 1 along the horizontal axis there. And by the time when it gets to +1, it's really back at -1 again. It's got back to its original position again, so it's going to repeat over length. And also, when you run this thing backwards in time, so if you imagine going back from 1 to 0, then you see that the bit from 0 to -1 is the first bit turned upside down. So it has exactly the properties that D'Alembert was looking for. But D'Alembert also realized that this is just only one of a whole family of curves which would solve his problem for the vibrating string. Clearly, a function which went twice as fast also had exactly the same properties. This thing repeats over an interval of 2L. And also, when you run it backwards in time, it goes upside down, as does sine 3x and sine 4x and 5, 6, 7, 8, 9, x. So here's a nice idea. It says that the sine waves are exactly the sorts of things that will form the solutions to my problem of the vibrating string. And once more, D'Alembert also thought something actually really quite clever too, that he realized that it's not just each one of these functions which could be a solution to his problem, but any combination of these sine waves would be a solution to his problem as well. Any combination, like 3 times the first one plus 2 times the second one plus 1 times the third one, any combination of these things would also have a period of 2L and would also turn upside down when you ran them backwards in time. So any combinations of these things would also be a solution to the problem of the vibrating string. And I think we've got a little demo here. So here's a vibrating string which we pluck. You've sort of seen this already, the string vibrating. But what we can also see, though, is that really what we've got in this vibrating string is just a whole series of sinusoidal vibrations added together. In other words, this is really what D'Alembert is saying, that any particular vibration of the string can be described. The vibration of the string could be described as a combination of sinusoids. Okay, so there's one problem that D'Alembert couldn't solve. And the problem he had was, imagine I have this string and I know exactly what it is in its initial state. I know I've displaced it, so I know exactly what shape this thing is. What sine waves do I need? I know that sine waves are good solutions to the problem when this thing is vibrating, but given that I'm starting from a particular position, what sine waves do I need to describe this particular configuration, this particular shape? And D'Alembert couldn't solve that problem, and that's quite a tricky problem. And to solve that problem, we need to introduce our second famous mathematician, and it's probably the most famous mathematician in the history of mathematics, certainly the greatest 18th century mathematician. He was born in Switzerland, did most of his work in Berlin and in St. Petersburg. He's the person who gave us the symbol E to represent the exponential function. He's also invented the symbol I to represent the imaginary numbers, and even the notation f of x comes from his work. So I'm sure you all now hope you've identified him in your mind. So yes, we're talking about Leonhard Euler. Leonhard Euler was a really remarkable man. And he said that he published over 900 mathematical articles. He was churning them out at one article a week in the last half of his life. His collected works occupy 70 volumes in the library. And half of his work was done after he became blind. So just to make you feel a bit low about yourself. So Euler was a tremendous person. So I'm going to tell you a bit about the story of Leonhard Euler solving this particular problem of D'Alembert. And maybe for Euler it was just a trivial thing. We don't know. But from the story of the Fourier transform, it's a really important part of the story. So let's have a look at what we did. So Euler has this idea from D'Alembert. You've got some function which is the shape of your vibrating string displaced at some particular point. And what you want to find is so much of sine x plus so much of sine 2x plus so much of sine 3x plus so much of sine 4x. So how much do you need of each of these sine waves to make this particular shape? How do you add them together to make that particular shape? In other words, you want a general formula which says, given f of x, this shape that I started with, what are these coefficients b of k? Now, we said Euler was a genius, and perhaps he went about solving this problem in a way in which mere mortals would not address. So Euler says it's very hard to solve this generally. I don't go into too much details, but there's lots of bad ways of trying to solve this problem. You can create expand all the sine functions as power series and then collect terms in powers of x, which is just a nightmare. Or you can set up get a fixed number, a finite number of samples of x, and set up a large set of simultaneous equations and try and solve those, and that's a nightmare as well. But Euler has this genius, so he has a different way of thinking about it. He says, why don't I stop trying to think about the general problem b of k and just address, could I find the value of one of these coefficients? And let's just assume a single and an arbitrary one. Let's say I'm going to try and solve for the third coefficient, b3. So what does he do? Okay, well, let's take our function f of x and we'll multiply it by sine 3 of x. This seems obvious to Euler. And so we're going to try and find b3. And so clearly I've got f of x sine 3x on the left-hand side, and then all the other components are now being multiplied by sine 3x. And now Euler says, well, it's obvious what you should do next. The obvious thing you should do next is try and integrate this between 0 and pi. Again, this is obvious to Euler, but not necessarily obvious to us. So when he does that, he says, okay, I wonder if this is taking me in the right direction. And he looks at this first term on the left-hand side. These are infinite series, by the way, so this makes the problem quite hard. So he looks at this first problem. So this is sine x times sine 3x integrated over 0 to pi. And he does the calculation and he finds it's equal to 0. Oh, that's nice. Scratch that now. So that looks like I've got sine 2x times sine 3x and 0 to 0 to pi. Well, that one's equal to 0 as well. And then he looks at, well, this one is clearly not going to be equal to 0 because sine 3x times sine 3x is sine squared 3x, which is positive, so that's always going to come with some positive thing, so let's leave that for later. Let's have a look at this next one, b4 sine 4x times sine 3x integrated with 0 and pi. That's equal to 0. In fact, you can carry on the whole story and you find out, look at all the other ones up to infinity, and they're all equal to 0. So magically, he's turned this infinite series into a very simple expression which simply relates this thing on the left-hand side to this thing on the right-hand side. And the only unknown is f of x and b3, which is what he set out to solve. So he's able to rewrite this then as, here's the thing on the left-hand side, here's the thing that's left on the right-hand side, and this can be evaluated. This is just the integral to 0 to pi sine squared 3x, and this turns out to be pi over 2. And of course, you can not only do this for the third coefficient, you can carry on the whole process with any of the coefficients, so you end up ultimately with a general formula which says if you want the kth coefficient, all you've got to do is integrate your function with sine k of x between 0 and pi, and then multiply, and you've got the bk coefficient. And I imagine that Euler was really pleased about finding this. And D'Alembert hadn't been able to do this. This is probably something on a Wednesday afternoon he managed to knock off. And so imagine the situation. I think he must be quite pleased with himself. He calls over his wife, Katerina, come and have a look at what I've just managed to do. And I've solving the problem for D'Alembert's coefficients by try and multiply by sine 3x integrated from 0 to pi. And look, I've now got this general formula for the coefficients of this sine series. And Katerina says, well, I can see that, but isn't that obvious? It's because the set of functions sine nx are orthogonal, and so yes, you must be right, and so that's he now understands what the real problem is. Okay, so Euler's got this formula now, which is telling you what sine waves you need to make your vibrating string, given its initial displacement. That idea, though, there's one other little germ of an idea in this, which wasn't apparent to Euler, but was apparent to our next mathematician, Daniel Bernoulli. If you've heard the name Bernoulli many times, that's because there was more than one Bernoulli. There was also Nicholas and Johann and Jacob. There was quite a family of Bernoullis. So this is the one we're talking about, is Daniel. And what Daniel said, it's quite interesting, this idea that the vibrating string is made up of these sine waves added together. Because maybe what's really happening is that the sine wave has the vibrating string has certain modes of vibration. Right? It has a mode in which the center part vibrates and the ends are stationary. It also has a mode in which the quarters go up and down, and the middle is stationary, and then likewise in 3/3 and 4/4 and 4/5 and so on. So really what you're seeing is not just an accident that it's sine waves, but the fact that this is a physical consequence of the way in which the string vibrates. It vibrates in a series of modes. How much of each mode you've got in the vibration is effectively the coefficient of the sine wave that Euler finds with this formula. Curiously, Euler and D'Alembert don't like this solution. And you've got to go back a little way, because I said that D'Alembert had this differential equation. He was trying to find functions which fitted this differential equation, and he thought that sine waves were one possible way of solving that equation. And when Euler finds his formula, he does the formula, this is the formula for the sine wave solution of D'Alembert's problem. But both Euler and D'Alembert felt that there are many other solutions, we just hadn't found them yet. Whereas what Bernoulli is saying is that no, this is the way the string vibrates. It vibrates as sine waves. Therefore, all solutions to the vibrating string are a superposition of sine waves. See, the key argument here is whether the sine wave superposition is a solution, or whether all solutions can be described as a superposition of sine waves. Okay, so that's going to come back to haunt us later. So now to bring in the main man. Jean-Baptiste Fourier was born in 1768. He was the 9th child of a tailor. He too was orphaned, but he was 10 years old when his father died. Had a brilliant school career. He won various prizes at school. And there's one interesting thing about his biography, which I think tells you a bit about maybe his motivation and his ambition. When he left the school, he wanted to join the artillery. He thought, I know a lot about mathematics and dynamics, and this would be really useful to be able to guide shells and things like this. And so I really think I want to do is my best contribution I can make to the country for me to join the artillery. And he was turned down because he was he wasn't of noble birth, therefore he wasn't allowed to join the artillery. I don't know about you, but I think that tells you something, that man is now going to say, right, I'm going to show you that I can be better than you. And of course, this time in France is a time of immense political upheaval. Remember, 1789. So he was born in 1768. 1789. He was only 21 years old. That's the fall of the Bastille and the People's Republic and the Reign of Terror and so on. Was actually active as a revolutionary committee in Auxerre, and they had a bit of a falling out. There's a lot of kind of groups that were for and against various things. It was a very unstable time, and unfortunately, by 1794, so again, what would he be then? He'd be 26. He was in prison. And so he was really facing the guillotine as well. So it was really quite fortunate for him that the whole government of France also fell apart in 1794 with the death of Robespierre, and he managed to be pardoned. And so he came out of prison and he got a job in the university in Paris. So this is what one does in those situations. So he goes to Paris and he gets a job. And there's just some people around in Paris that also have a sort of interest in mathematics. One of them is called Lagrange, and the other one is called Laplace, that just happen to work in this university. So he happens to just stumble into a university which has two of the great French mathematicians of all time. And eventually he becomes a chair of analysis and mechanics, and followed after Lagrange in Paris in the École Supérieure or something, forgotten the name, Polytechnique. Okay, so when the terror comes to an end in 1794, then another figure comes on the stage and starts to sort out France, and that figure happens to be called Napoleon Bonaparte. So around about 1797, Bonaparte decides to take all French civilization and culture to the Egyptians, because he thought the Egyptians could do with it. And so he sets up this scheme to take the army and a whole series of advisors and scientists and mathematicians and language experts, take them to Egypt and set up institutions of education in Egypt. This is what he wanted to do, take the white man's burden to the underprivileged nations of the world. So Fourier decides to join him. He's a professor of a university in Paris, but he says, "Oh, I'll come with you to Egypt." Okay, maybe it's just ambition again. He wants to just do something. Unfortunately, in 1798, Napoleon has a bit of a setback. The entire fleet is sunk in the Battle of the Nile by Admiral Lord Nelson. So another figure in our story perhaps we weren't expecting. Napoleon decides has enough of Egypt. He goes back to France and he becomes emperor. But Fourier stays in Egypt, and he becomes quite enamored with it. He becomes quite an Egyptologist. And there's another whole career of Fourier that's not part of this talk, which is about his work in Egyptology. And he even has a role in the recovery of the Rosetta Stone and supporting the decoding of the Rosetta Stone by Champollion. So there's another whole book to be read about Fourier's work in Egyptology. Fourier finally comes back to France in 1801. He'd like to go back to the university, but Napoleon years for him says, "You were very good in Egypt. I want to make you prefect of the department of Isère," and Isère is basically Grenoble, the area around Grenoble in northern France. Fourier does a pretty good job. He seems to have been quite popular as the prefect of Isère. He drains swamps to make the area more habitable and reduce the amount of disease. He builds a road across the Alps, which if you next time you drive across the Alps, you look for the N91. That's the road that Fourier built, not personally, presumably. And as prefect in Isère, he takes up an interesting mathematical problem, and it's the problem of the propagation of heat. So he starts at about 1804. I can find my bar demonstration, so we can try and have a bar here, which we heat up, so the colours meant to represent the heat of the bar. And the problem essentially is this: imagine you've got a bar which is heated up, and you let the bar cool. Then obviously the heat in this bar gradually goes away. The temperature goes away eventually to ambient temperature. But something is slightly more sophisticated than you might think, because clearly if I've got my original bar, which is hot in the middle and cold at the ends, then I've got heat flow along the bar, as well as heat flow being lost, as heat being lost. So I've got something which is happening both in space and in time. Right? The temperature of this thing is changing both along the bar as heat flows along the bar, and also in time as heat is lost, as the temperature is lost. This might ring a few bells, the idea of differential equations set in space and time. So within 3 years, Fourier had done a really good analysis of this whole problem of the propagation of heat, and he created a paper which he presents to the French Academy of Sciences in 1807. And of course, he's quite familiar with the people who run this kind of thing, since he studied with Lagrange and Laplace. And for some reason, I don't really know the story, but it seems to be highly suspicious that in 1811, the French Academy of Sciences decided to have a competition for the best theory for the propagation of heat. So they have this competition, and surprisingly enough, Fourier decides to submit for this competition. And there's only one other entry to the competition. So you think something's fixed somewhere along the line. So that 1811 monograph that he submits to the competition is the first monograph where we find what we now call the Fourier transform. So it's this particular point that we see published what we now know as the Fourier transform. There's a picture of the storming of the Bastille, and there's Napoleon in Egypt. Here's our cooling bar, and here's our original paper from 1807 on the propagation of heat. So when we look at this paper and we say, well, what sort of formulas has Fourier derived for describing the propagation of heat in a bar? And he says, well, first of all, I'm going to describe how the temperature profile of the bar as a function of its position can be described as a superposition of sine waves. Sound familiar at all? And then, once you've got a profile of this heat through the bar, you then need a formula to find out how much you need to make that profile. And this is the formula that you need. Does that formula look at all familiar to you? So it turns out that what Fourier managed to do, almost without referring back to the previous work of D'Alembert and Euler, was to recreate the work of D'Alembert. Now, we don't exactly know how much of this he copied and how much of this was his own work. The only thing we know about Fourier's work in here is that it's full of mistakes. So we suspect he didn't do it by copying Euler, right? Since we know Euler, Euler knew what he was doing. So Fourier makes these three things then. So first of all, you can represent the temperature profile in a bar by a sum of sine waves. That in itself seems a bit weird. I mean, the vibrating string makes sense. Remember, the modes of vibration of the string gives you sine waves, so it makes sense to describe sine waves as a superposition of sine waves. It doesn't make sense for a temperature profile, because that could be anything you like. It doesn't have to be. There's no modes of vibration. So that seems a bit weird. He comes across Euler's formula, but he derives it with some very strange mathematics. And he also makes Bernoulli's interpretation, which is that all possible temperature profiles of all possible bars can be described by sums of sine waves, which is Bernoulli's idea that everything can be described as a sum of sine waves and not just a subset of possible solutions. So the Academy sets up a committee to study the responses to the prize challenge. There were 2 submissions, and they decided to give it to Joseph Fourier as a winner of the prize. But however, they really didn't like it. There was quite a lot of criticism of the approach that Fourier had taken and the mathematics in it. Now, the mathematics are not. I mean, I'm not that good on the math side of this. So I'm indebted to a modern mathematician, Rudolf Langer, who did a study of Fourier's papers and is trying to work through exactly Fourier's thinking and try and find out exactly where Fourier was going wrong. And where the sort of mistakes that Fourier was making and so on. And this is just one part of Langer to recommend to you if you want to find more details on the mathematics. So at some point this is just a sort of an example, at some point in Fourier's derivation of Euler's formula, he has this expression on the bottom. You just about see there's a pi symbol, which means a product, a continued product. And it's a whole product of a series of numbers. Obviously, such a product gets big quite quickly, but it gets very big very quickly if that's an infinite product. So as r goes to infinity, then this thing on the bottom gets really, really, really big because it's a product of all the numbers up to infinity. And that, generally you have to worry about things like that. So that very, very quickly this whole thing will go to 0 because the bottom, the will rapidly go to infinity as r gets bigger and bigger. And this is just completely wrong. And as Langer says, although there's no conclusion other than that the vanishing would be logically admissible, but Fourier had no intention whatsoever of drawing that conclusion, and hence he proceeded undismayed with this formula. So even though this formula is clearly bonkers, he then carried on, and he found a solution which essentially, well, I know what I'll do is I'll add another infinite term in the numerator, and then I'll cancel out the infinite terms. Right? This is generally not good practice, by the way, if you're following things in mathematics. Now, I need to hurry up this story. So the thing was that Fourier had come up with this kind of sort of piece of physics, which which in a way was a recreation of things that had gone before, and it needed something to be sorted, things needed to be sorted out. And to sort out Fourier took a long time. So mathematicians that came after Fourier looked at this problem, and they were better mathematicians in the sense that they were able actually to address this problem. So let's have a look at some of those. The first one name is Johann Dirichlet, and he tackled head-on this problem about a graph and a function. What's the difference between the shape of something, the shape of the string, and a function, some sort of mathematical expression? And is there a difference? So to Euler there was a difference, that you could have an expression like a sum of sine waves, but he would also say that there could be shapes which are not a sum of sine waves. So in other words, that there's a difference between this graph, the shape of the string, and the actual algebraic expression for a sum of sine waves. Dirichlet showed that that distinction is not valid, that effectively all things that are graphs are also functions. All a function is something which allows you to assign a value to all numbers on the real line. So as long as you've got some function which takes a value x and produces a single finite value y, then you've got a function. And that function doesn't have to be the same for all points along the real line. It can be made up of little bits and pieces, but as long as there's some kind of a rule which generates a y for a given x, then that's all you need from a function. And Dirichlet's most famous function is this one, the modified Dirichlet function, which basically has if you've got if it's irrational, it has the value 0, and if if the real number is a rational number, then it has a value non-zero. And so this graph just goes up and down, goes up every time it hits a rational number, and down every time it hits an irrational number. And of course, in any finite interval, there's an infinite number of rational and irrational numbers, and so this graph goes up and down an infinite number of times in every finite interval. So it's a pretty weird function. But Dirichlet showed that even this function fits the Fourier transform. In other words, you compute the Fourier transform of this, and it works. So this is a very weird function. And so if there are any graphs which don't fit the Fourier function, more weird than this one, than this particular function. To cut a long story short, we then have like another 100 years of mathematics, again involving a whole series of really famous people. So we have not only Dirichlet, but we have Riemann, we have Lebesgue, we have Kolmogorov, we have Hilbert, all trying to address this problem about what particular types of functions actually could be put through the Fourier transform satisfactorily. So it takes us right into the 20th century, each time showing that the Fourier transform could be applied under wider and wider conditions. I just want to end with one last point in the history, which is in 1965. So we're now 1642. We're now at 1965, and these two gentlemen. I think Cooley is still alive. Tukey's not those. So this is Cooley and Tukey. By 1965, we had digital computers. And somebody says, wouldn't it be nice if we could do the Fourier transform in a digital computer? And it turns out that it's a real pain to do because it's very, very inefficient. The Fourier transform takes an awful lot of multiplications and additions to compute on the Fourier transform. And then basically, we can come back to the formula. We can kind of see the reason. So we've got to see the reason why we've got to do. This formula here. We've got to do for every v, so for every coefficient, we need to do this integral over the duration of our function from between 0 and pi. So that's a whole series of multiplications and additions that we have to do. We have to do that for every v. So if I've got 1,000 of these to calculate, and this is 1,000 samples long, I've got 1,000 times 1,000 multiplications and additions. I've got a million computations to do. So what Cooley and Tukey said was, well, this is the sort of the general problem. I've got, if I've got n samples I want to do the Fourier transform from them, say I've got 1,024 samples, then I'm going to need to do 1,024 coefficients. Each one of those is 1,024 multiplications. So I've 1,024 squared calculations. What Cooley and Tukey said was, well, imagine I could take this great long series of numbers, 1,000 numbers, what happens if I found a way of calculating, to do the Fourier transform of the first half, and then the Fourier transform of the second half. And imagine there was some technique where I could take those two Fourier transforms and somehow mangle them together in a very cheap way and get the overall transform of the whole thing. So effectively, rather than doing n squared, I've got two lots of n over 2 squared. Make sense? Okay. So if you do the math, so I've done the first half n over 2 squared, the second half n over 2 squared, then I've got a bit jiggery pokery to put them together to get the overall thing. So I've got n squared plus 2 squared over 2 squared plus n squared, and that turns out to be 500,000 calculations, which is about half. So I've saved half of the computation by this process of doing, instead of doing the whole thing, do it in 2 halves. But then of course you think, well, you know, why do I stop there? You know, why don't I take this half and it's 2 quarters, right? Okay, so we're doing 2 quarters, so I've got 4 lots of n over 4 squared plus 2 lots of n over 2 plus n, and now I've halved the amount of computation again. And why stop there? You know, you can carry on doing it in 8/8, or ultimately, if you've got 1,024 samples, you end up doing 512 transforms of size 2. And a transform of size 2 is basically just a couple of multiplications, so it's not a very, very easy thing to do. And what you end up doing is transforming the amount of computation that you need to go from this 1 million computations down to 12,000 computations. The amazing thing about this algorithm is when you think of how fast Fourier transform against a normal Fourier transform, you think that, you know, it's a bit faster. It's, you know, it's twice as fast, or it's 5 times as fast, or 10 times as fast. This is 100 times faster. Right? It takes 100th of the computation of the full algorithm, and it comes up with identical outcomes. So the computation at the end is identical. So I think I've got a little demo of that as well. So here's a waveform, a recording, and hidden in this waveform is a sine wave. Oh, I'm sure you can see that very quickly. One way of finding the sine wave in this noise is, of course, to compute the Fourier transform of this waveform. So we'll compute the Fourier transform using Joseph Fourier's way, and there it goes. And there you can see this is the spectrum of the sound. So these are the individual Fourier components. We call them frequencies, and this is the size, which is these BK coefficients. And you can see that there, this particular frequency, I've got a large component there. You can also see that it took 6,374 milliseconds. It took 6.5 seconds to calculate. So that's the standard way of, that's the Joseph Fourier's algorithm for doing it. So if we do it with the fast way, then it takes 8 milliseconds. Okay. That's the difference, and that's the important thing about the Fourier transform being part of modern life and modern technology. It's not just that it's a Fourier transform, but it's also being able to compute it in a very rapid and efficient way. So it's a very important part of the story. Okay, I'm going to round up. I can't play these audios, but just to show you that this is again a kind of a application. I was going to play you an audio file before and after it was compressed, and show you that it sounds exactly the same. But you can have a look at these 2 images. These are 2 images of Buttermere, and this image is 488 kilobytes, and this image is 63 kilobytes. And you'd be hard-pressed to see any difference between them. And again, the Fourier transform is basically used to take away those aspects of the image that you can't see because they're outside of your resolution of your eyes. So by solving this problem in the spectral domain, the frequency domain, you can compress this image down to the bits that are important for you to look at and take away the stuff that you can't see. Okay. I've told you the story, the history of the Fourier transform, and I've said that the really key players in the history of the Fourier transform are D'Alembert, Euler, Bernoulli, Dirichlet, Cooley, and Tukey. You notice in that list it doesn't have Fourier's name in it. So there's really one still kind of elephant in the room here, which is, why do we call a Fourier transform the Fourier transform? And so there's got to be a reason for that, and I think this is really the exciting part of the whole story. And this is why, you know, I thought the Fourier transform makes a very nice talk. Fourier did something that nobody else did. He looked at this formula and he asked the question, what does this formula mean? See, Euler was a fantastic mathematician, but mathematics was just kind of symbols, right? He was just a fantastic way of manipulating the symbols. D'Alembert was looking at this, and he was very happy to have a formula which gave him the size of the sine waves, but he didn't look at the formula. He said, look at this formula, what does it mean? What are you actually doing in this formula? And Fourier said, what is going on? What is this formula actually doing? So he says, okay, well, what really I'm doing is I'm taking f of x, that's my shape of my graph, I'm multiplying it by a sine wave of some particular frequency, so that's going to give me a kind of a sort of a shape like this. And then I'm integrating it from 0 to pi. Well, what's that? Adding up all this pink area, basically. I mean, it's basically just finding the area under the curve. That's all an integral is. So Fourier says, well, obviously, if you want to know when this formula applies, this formula will apply any time where you can calculate this area. As long as you can calculate this area, you can use this function. So it's not only those situations where you've got modes of vibration of a string. Any situation in which you've got a shape, you can apply this formula. It tells you how much of a sine wave you need to be able to build the shape. And it doesn't really matter whether this function f of x is discontinuous, whether it's made up of 3 different bits, whether it's got jumps in it. All that matters is as long as you can calculate the area, you can apply this function. And that is something that hadn't occurred to people previously to that time. And but that wasn't the end of it. There's another thing that he looked at, and he said, well, this thing only integrates between 0 and pi. In other words, I'm only interested in my function over if this is my hot bar. I'm only interested in the temperature profile over my bar. I don't care what the temperature profile is in Birmingham or in Jupiter. I'm only interested in what happens in my bar, right? So I'm only interested in the bit between the length of the bar that I've got to play with. So it says a formula to anything over this interval, and you don't care what this function does outside that interval. You can do anything you like, right? Because the formula just says add up the area between this bit, this point, and this line. What happens outside the area has got nothing to do with this formula. And so Fourier says you can apply the formula even to functions which do completely different things outside the area of interest, and they have no influence on the formula at all. Whereas Euler always wanted functions to be defined over all the real line. So what Fourier gave us in a way is not the formula, or the concept of superposition of sine waves. He said, this is really what it means. This is what you're doing when you're applying this formula. Go back to Rudolf Langer's paper again. Fourier's work has the profoundest effect on the development of pure mathematical concepts and the extension of the range of mathematical applications to the sciences and technology. But these outcomes spring in the main from Fourier's interpretation rather than from his mathematics. It's the way he interpreted the mathematics which was novel. And Langer then really makes this really nice point, which is it's maybe because Fourier wasn't a great mathematician, maybe because Fourier was stumbling in the dark a little bit, he was able to make this imaginative leap. Partly because of his very disregard for Fourier, he was able to take the conceptual steps that were inherently impossible to men of more critical genius, like Euler and D'Alembert. Maybe simply because he was stumbling through, and he just hit upon an interpretation which just turned out to be correct. 100 years of mathematics down the line proved to be correct, but he just stumbled on. He was the first person to have that particular interpretation of the formula. So we've come to the end of the story. Fourier is, of course, very famous. We've heard of him. We've heard him not just for the Fourier transform and the Fourier series. There's Fourier's law of heat conduction. He was made a member of the French Academy of Sciences. Well, at the second attempt, the king refused his admission the first time. He's a member of the Académie Française. His name is one of the 72 great Frenchmen whose name is inscribed on the Eiffel Tower. And he even has a university named after him, the University of Joseph Fourier, which is cited appropriately enough in Grenoble, which is where he was prefect, of course. So I come to the end of the talk, and now I think you can see that there's a sort of this title has 2 meanings. firstly, we've said that Joseph Fourier, his insight was that you could apply the transform everywhere. You could apply it to any function at all. There was no limits to the sort of function that you could apply. The Fourier transform would work in that situation, and that he was the first person to propose that that was the case. But also, in doing that, he made the Fourier transform applicable to many problems, and of course that makes it the reason why we're using we have the Fourier transform in all our technology today. So Fourier was either a genius or he was very lucky. If you want to follow in Fourier's footsteps, make sure you have his genius or his luck. Thank you very much.
Thank you, Mark, for a very interesting and well-researched talk. We've got time for some questions, if anyone would like to ask anything or any comments. James?
So I think you credited, was it Euler's wife with the sort of observation of sort of orthogonality?
That was a joke.
I know. I suppose I'm interested in the idea of orthogonal basis vectors or bases, and when that starts to emerge in the sort of common understanding of, so it's up to you really whether you describe things in frequency space or spatial or temporal space, basis, and if you could just do it one or the other and they're equivalent.
Yes, exactly. I mean, so the idea that you can create a set of basis functions and find a set of coefficients which would describe it, that then just turns into like what we now call principal component analysis, or non-negative matrix factorization, or something where you just create that you've got some data and you want to say let's describe the data in terms of these bases. I don't know anything about the history of those things. I can't answer you a direct question in terms of history, but you're absolutely right that once you started with something like the Fourier transform, you could do that with any other kind of basis. So we have wavelets and Hadamard. My brain's going. Dirichlet had other.
I was thinking a set of wavelets.
We're getting out of our depth.
No.
Remind me something.
I was looking at you, Mark. Do you know anything about them? The history of orthogonal basis functions?
Well, I suppose they were. They all come down to differential equations.
So
differential equations. I suppose they were developed in the 19th
Dirichlet was probably before Stillman knew them.
Laguerre. I mean, starting in college, differential equations, aren't they? And Laguerre, Legendre, Hermite, all these. They've all got different. They're all orthogonal. Yeah, they're all orthogonal with different weight functions, aren't they? Yeah.
So this is going sort of 18th century.
Yeah. Well, I suppose it's Hilbert spaces is the abstraction, isn't it? Fourier theory. Fourier.
Any more questions or comments or?
Maybe. Where does this notion? I mean, the thing you demonstrated of the sound with a sine wave hidden in it. The signal, the Fourier transform looked about as complicated as the original signal.
Yes, it doesn't lose any information.
Yeah, and yet there's this notion that packaging information in the Fourier transform is often more efficient, and that's why our brain does it.
Yeah. So in the sort of MP3 compression idea, or in the JPEG image compression idea, is that the image will have the audio will have frequencies, or the image will have spatial frequencies, which effectively you don't perceive. So you could take those out, and the sound will sound exactly the same, and the image will look exactly the same. It's a completely different sound, and it's a completely different image, but it has the same perceptual effect. And this is effectively what the Fourier transform is: takes you into a domain in which you can perform those manipulations. So that's how you could get rid of the bits that you don't want. It's great. In audio, it's quite clever, really, in that. You've got the sound that's come out of the recording studio, or when people play their instruments and singing and so on, and you say, I want to put this onto my MP3 player. So what I've got to do is make a completely different sound. Start with this one, and then make a completely different sound, but which to a human being sounds exactly the same. And when you think about it in that way, you create a sound which is not the same as the original sound, but the waveform looks completely different, and yet when you listen to it, it sounds just the same as the original sound. You're taking out all the bits that effectively that your human being can't hear in the sound, and that allows you to throw away a whole load. It actually allows you to throw away 90% of the sound before it actually starts. You actually start being aware of the bits that have been dropped.
I was coming at the question from the other side. So I'm a neuroscientist, and I'm interested in why. Essentially, what our brain does is the brain decides to throw that information away. That's why you can throw it away when you want to compress the sound.
No, it's more. There probably are some aspects of brain function, but it's more peripheral than that.
Yeah,
it's more the sort of filtering that goes on in the cochlea, or the sort of neural firing in the visual cortex, in the retina. So I mean, it's more that all sorts of spatial frequencies are lost.
Yeah, for vision it's definitely in the cortex.
Yeah.
But
and
the question is then, all that information that's there in the natural image, we can throw away, both from a computational point of view and presumably from an evolutionary point of view, because it's not relevant to us. So how come that we can compress an image into so much smaller a package in the frequency domain and it still contains all the relevant information, yet in the space domain it's a mess?
So I mean, again, when you're looking at an image, the image may be fluctuating in intensity at a rate which is in spatial frequency is too fast for you to see.
Yeah.
So you can get rid of that, and that's certainly true in the color information in particular, because the density of color cells in the retina is much lower than the densities of the rods to do the black and white, the intensity detection. And so typically you will reduce the sampling rate for the color information to much lower spatial frequencies than the intensity information. So that's the kind of changes you make to the image, such that it will look the same, but it will actually be a different image. So it's just saying what can you see and what can't you see in the image.
Would filtering low be enough? Because that's effectively what that is doing, isn't it? Just filtering it.
So then Martin wants to have a word. He's going to change the subject.
Yeah.
Sorry, no, it's just continuing on with what you were saying. You were saying if I understand your question right, you were saying why is it possible to filter in the frequency domain but not in the time domain, in the original?
Why is it possible, but why is it so much more efficient?
Well, forgive me but surely the whole point of splitting the thing up into different frequencies is that you're performing a sorting out. It's like you've got, like you're tidying up your room and it's a total mess and you don't know what's rubbish and what isn't. The Fourier transform, as I understand it, is a sort of putting things which are rubbish in one area and putting things which need to be kept in another area, so that everything that's rubbish can then be efficiently chucked into the bin bag. Would I be correct in saying that? Do you think?
Yeah, I mean, I was just thinking of another solution. Maybe another problem is generally you can do filtering. You do filtering in the frequency domain or in the time domain. It's just more efficient in the frequency domain. So you can do it in the time domain, but it involves the process of convolution, which is mathematically expensive.
Yeah.
The Fourier transform, the full Fourier transform, is as expensive as convolution, but we have the fast Fourier transform, which is 100 times faster than n log n rather than n squared. So it's much more efficient to do. So by taking your problem into the frequency domain using the fast Fourier transform, solving it more efficiently there, and then bringing it back, is actually cheaper than trying to solve the problem in the spatial domain or the time domain. But there's nothing fundamentally in principle why you couldn't do it in either domain. It's just much more efficient to do it in the frequency domain. I think that's probably.
And I suppose evolution is good at figuring out what the more efficient process is.
Well, I mean, whether the brain, I don't know that you'd want to say that the brain does Fourier transforms. The ear is a very special organ for sorting out frequencies, but then that's actually a mechanical device for sorting out frequencies. It's better described as a series of filters.
Just offer a quick insight. Sorry, just to. I think the natural world doesn't use all frequencies equally, and so the Fourier transform and what JPEG and so the lossy JPEG does is enable you to sort of be selective about which frequencies we use. If we did live in a world, a Martian world, where visually or temporally all components are independent, then you couldn't take any shortcuts.
No.
You'd have to just encode the original pixel values of the temporal code samples as in the to the full resolution.
And any compression would then lose lots of percentage.
So does that mean that there is a loss of perception in the fast Fourier transform? It's just it's not a perception we can see, so it makes no difference. Or
suppose if you had
or is the fast Fourier transform giving exactly the same results as the
the fast Fourier transform isn't an approximate form of the Fourier transform. The fast is exactly the same as the Fourier transform, but it's just a very efficient algorithm for computing it.
So there's no loss.
It's no loss of precision of the actual result.
Could you just explain how fast Fourier transform shortcuts that again? I know that was part
well, I did fudge it. I must admit, I didn't give you a lot of detail, and I probably can't in the amount of time I've got available to you. But essentially, the idea is that if you want 1,000 coefficients, then you've got to do 1,000 operations, and each operation will require 1,000 multiply adds, so you end up with 1 million calculations you have to do. But what Cooley and Tukey found was that if you divided your sequence into 2 halves, you could compute the Fourier transform for each half, and then there's a very simple process of adding and subtracting the results there, and you end up with the original, the full one. So you can compute the full one by computing 2 halves and then mangling them together in a very simple linear operation, not a very expensive operation, cheap operation to mangle them together to make the whole thing. But once you've done that once, you can do it again. So you take the half, you can do it 2 quarters, mangle the results to get to the half, and then mangle those 2 halves to get to the 1, and then you can keep on right the way down to the bottom. So ultimately, at the bottom end, you just do transforms of size 2, which it's adds, and you've done a transform of size 2. It's trivial to do. So then you just build up the
transform of size 2. Is that just?
Well, it takes you two samples in time, two samples in frequency. Yeah.
Presumably, though, you need to have a power of 2.
So that's very nice. Yeah. So it's worked. So if it's not a power of 2, then of course you get stuck. So if you start at 150, 25. So, but if you start at 128, maybe 128, 64, 32, 16, 8, 4, 2. Right, I've gone all the way down. So that's why when people do the Fourier transform, they prefer to have a power of 2, because that way you can come down right the way down. You get the most out of the Fourier transform, the fast algorithm.
Or of course you could truncate it to the largest value of 2.
Actually, people do it the other way. Is they say, okay, I've got 600 samples. I'll just make it up to 1,000 with zeros. Which you think would slow you down, but the fast Fourier transform works so much better with 1,024 than it does with 600 that you see enormous gain as a consequence. Right. So you go up to the next
You can generate artifacts though, can't you? When you do that, if you either set or extend it.
Yeah, exactly. So you're right. You're now not transforming the original sequence. You're now transforming the sequence padded with a whole lot of zeros, which is a different sequence to the one you started with, and then you get all kinds of spectral problems as well. But that's true. And there are, there's all kinds of other Fourier transform work. That's 1965. After that, there's a whole lot of other work in this area where you can do effectively apply these faster algorithms on arbitrary length sequences. So it's not just limited to powers of 2 if you go to more modern algorithms.
I have seen some sort of performance analysis where instead of pairs and pairs of pairs, they do it in triplets and so on. But and I think in theory, triplets will be more efficient. It's just so much messier. It's much easier to stick with powers of 2. I think the optimal value of n for the multiplying up would be something like 2.6, but that's not practical now. So 3 is marginally more efficient than 2, but it's messier. But that was a long time ago, and I can't find that reference anymore. Any more questions?
I'm sorry to monopolise this a bit. few years ago, before I came here, I used to work in the high-speed networks group at Loughborough, and a lot of their work was involving image compression using discrete cosine transforms.
Oh, yeah.
How are cosine transforms related to Fourier?
Yeah, so I fudged the arithmetic of this a little bit. I only just talked about sines, and really, strictly speaking, I've ignored one particular aspect of Fourier. Yeah, so a cosine transform is really just the same thing with cosines rather than sines. There's nothing really terribly magical about it. It's just a series of very similar formulae.
Why would you use cosines?
With cosines instead, yeah. So
right. Why would you use cosines though instead of Fourier?
So the problem with this formula, as I've stated here at the moment, is I've got the amplitude of the coefficient of the sine wave, but I haven't told you anything about the phase of the sine wave. So I've completely fudged the issue by not mentioning that, because I only have an hour and I still went over that. So generally you need to solve this with both sine waves and cosine waves, and that gives you both the size of the sine wave and the phase of the sine wave. And if you only use sine or you only use cosine, you get a size, but you don't get the phase relationship thing. And generally for a vibrating string that's fine, because you know the phase, because it's got to be, it's stationary here and stationary here, so you know all the graphs are going to be 0 here and 0 there, so you know they've got to be made up of sine waves. So for a vibrating string, it turns out that you only need sine waves, which is...
But if it was a non-repetitive function, would you then need both?
You do.
The sine
You need
Okay.
to know exactly not only the size of the sine waves, but you need to know where they are in the cycle at some particular point in the curve.
Okay.
Any more questions or comments?
Just like a comment on the why they were probably doing cosines rather than sines, because I happen to know that one. It's the cosine is 0 in the middle, whereas the sine is 1 in the middle. Okay. So if you're then taking somehow a spatial extent, which you need to do if you're compressing it. If you want the average to be 0, you're better off using the cosine than the sine, because otherwise you get a little artifact somewhere that can quickly add up and give you all sorts of problems with the mean lumens, say, if you're
Okay, well thank you.
So, as we said, compressing with the Fourier transform is getting rid of 6 frequencies that we cannot perceive with our natural sensors. What about the other way around? What if we could enable ourselves from perceiving frequencies that we do not, by mapping them to things that we can perceive?
Yes, absolutely. I mean, I don't know why people don't do this more often. You know about cochlear implants, right? So these are people who have electronically stimulated cochleas, and they typically have an external speech processor as a microphone, and this picks up speech frequencies and translates and excites the speech frequencies of the cochlea electronically rather than acoustically. So I thought, well, why don't these people give themselves ultrasonic hearing? Then they can hear bats and mice and and insects. And, I mean, there's no. I mean, once you've got this incredible device, right, with this computer in your pocket and direct electrical connection to your brain, it's a real cyborg device. Why limit yourself? Why limit yourself to 100 hertz to 5,000 hertz? Why not pick up radio waves or microwaves or I mean the sky's the limit, really. So it's all possible. It's all possible. But I guess people they prefer to talk to other people rather than listen to ultrasound, probably.
And probably your brain could only process so much at one time. It's got
you're still limited by the stimulator and the nerve firings that you're making in the cochlea. It would still sound like sounds in the frequency that we're familiar with, but of course the source would be sounds that you couldn't hear, right? So absolutely. I'm not that I'm intending to get a cochlear implant, but I'd love to have tried that.
Any other comments, questions? If not, I think we should thank Mark again for his very interesting talk. And I think there's still some tea and coffee available if anyone wants to help themselves. Otherwise, thank you for coming.